Okay, we've got about 5 or so more examples to do. Um, there's actually more than that on here. I don't think I'm going to do all of them. If there's interest and anybody really wants me to, I'll come back and finish off the packet, but the last couple of examples probably won't get done on this just because there's several more and I'm going to try and keep this to 3 videos, whoops, if possible. Okay, we're going to go back now to example 5. We want to find the volume that's under the paraboloid z equals x squared plus y squared and above the disk x squared plus y squared is less than or equal to 9. This one really isn't that difficult if you remember how your shapes look. The z equals x squared plus y squared, kind of sketch our three-dimensional surface here, is your basic paraboloid which opens up. So it's going to look something like this. And it just keeps on going. But what we're trying to find is the volume that's beneath this curve, so everything underneath of that surface, and above the disk x squared plus y squared equals 9. Well, that disk is nothing more than a circle, a circular base, right here. So, what we're trying to find is all the area between here and here, all the way around this thing. That's between this paraboloid and above this disk right here. So, I mean, it seems pretty obvious if you look at the domain of this thing, of the dA part, it's going to go from 0 to 2 pi. It's a full circle, and it looks like the radius here is 3, so it looks like it's going to go from 0 out to 3. So when we go ahead and set this one up, it should be a double integral, 0 to 2 pi for the theta, 0 to 3 for the radius. And remember that x squared plus y squared, see if I get this right this time, z is r squared. So r squared r dr d theta. This one actually should be very quick because this is really just r cubed dr. The d theta can be separated out. So 0 to 2 pi of d theta times 0 to 3 r cubed dr. So this is just going to be theta from 0 to 2. This is going to be 1/4 r to the 4th from 0 to 3. So this is going to be, not 2 pi. This is going to be 2 pi minus 0, so that's 2 pi. This is going to be plugging a 3 in. 3 to the 4th power is 81, so that's 81/4 minus plugging 0, and you get 0. So 2 over 4 is going to give us 1 over 2. So 81 pi over 2. Okay, and this just required that you actually remembered the basic paraboloid and what it looked like, and then the fact that this is just a circular disk that's on the xy plane. All right, number 6. Now we want to find the volume that's above the cone, z equals the square root of x squared plus y squared, and below the sphere, x squared plus y squared plus z squared equals 1. Excuse me, this one's going to take a little bit more visualization than the last one did. All right, so z equals x squared plus y squared. It says above that cone. So we're going to have some kind of here, let me use different colors for this one. I'm going to have to, I think. So we got a cone. Something like that. Okay, so we got this cone, so it's got to be above the cone, but it has to be below the sphere. X squared plus y squared equals plus z squared equals 1. That's just a sphere that the entire way around. So if we're talking about above this cone, no, we really only have to focus on the top half of the sphere. So you're going to have some kind of a sphere. Probably should have drawn the sphere first just to make this a little bit easier, but your sphere is going to come all the way down here, something like that. That's not going to work. Um, got a radius of 1, so 1, 1, 1. It's going to look something like this. Something like this. And I'm only really, wow, that's just horrible. All right, we're going to completely get rid of this. Try again. Here is my sphere. Okay. Okay, that'll make that a little nicer because that's pretty much going to be where the XYZ axis meets. Now let's try and do this, see if this works out. All right, something like that, I guess. And now we've got our cone that's going to come up here. Actually, the cone can keep extending forever. But what we want is above the cone, so above this part, I guess the cone should probably have stopped in here. Let's do that part again. Because it's got to be above the cone but below the sphere, so it's got to be a cone which probably comes out like this, and then something like that. Above the cone and below the sphere. So it's basically going to be the space in between here and up here. So that's what we're looking at. So if we look at the domain, well, the domain of this thing, really, if you think about it, it's going to be straight down from here. It's just going to be the circular region where this cone and this sphere hit. So it's going to be a circular region like this, which is definitely why we're going to do this in polar. We're going to have to do some figuring out here, though, as far as where these intersection points are supposed to be. All right, well, one thing I can see is that if we're going to figure out the intersection of this sphere and this cone, I'm going to have to either set them equal to each other, or I could just take Z, plug it in here for Z, and then figure out what the intersection points are there. So Z, plugging this in here, squaring it, is going to get rid of that square root. So what I'm going to end up with is x squared plus y squared. That's from these two pieces. Plugging this in for Z squares this, so it gives me another plus x squared plus y squared equals 1, which really gives me 2x squared plus 2y squared equals 1. Factor out the 2 and divide both sides by 2 gives you x squared plus y squared equals 1/2. Well, you still have two variables here, but remember we're changing this into polar, and x squared plus y squared is r squared. So solving for r is going to be 1 over root 2. We only use the positive there because the negative radius doesn't tend to make any sense. So really what that tells me is this radius of this circle right here on the domain is 1 over root 2. This is negative 1 over root 2 here. Just tells me that the values are going to go out that far as the radius is concerned. And then, of course, the whole circle goes 0 to 2 pi. So that pretty much tells me what we need to do as far as our integration is concerned. Let's set these up. So theta is going to go 0 to 2 pi. R, we now know goes from 0 out to 1 over root 2. Root 2, come on. There we go, a little bit of lag there. And then we're going to have to figure out what goes in here. R, dr, d theta. Let's see if that ever shows up. There we go. Weird. All right, so let's take a look back up at the top. So remember that this thing up here was z. Well, z equals, well, if it was x squared plus y squared, that would be r squared. But since we're taking the square root, z just equals r. And that is the top of this cone. That's the circular region right here of this cone. So that is really just a flat region. But then I'm taking the area between the sphere right here and this thing right here. So it looks like whatever it is, I'm going to end up taking whatever the area of the sphere is and subtracting the area between the cones. So the cone part is just r. Now we got to figure out what the sphere is. Well, that's just solving this thing right here for z. So we can do that over here. Z squared is going to equal 1 minus x squared minus y squared. I don't even know if I just drew a y there. Nope, not quite. Close enough. Um, that means that z squared equals 1. I'll wait for it. There we go. If I factor out the negative sign from just these two terms, minus x squared plus y squared. Of course, x squared plus y squared is r squared. So z squared is 1 minus r squared. Pretty sure I wrote that. Yep. This is a really bad lag right now. So z is going to equal the square root of 1 minus r squared. There we go. So that's the top of this circle right here. I'm sorry, the sphere right here. And so I'm going to take that 1 minus r squared and subtract the r piece, which is the top of this cone right here, because we're going in between the sphere and the cone. So there we go. All right, this integration is a little bit more messy, but really all it takes is a u substitution and some algebra, so we're going to run through it relatively quickly, I hope. This lag is not helping. There we go. Okay, everything's constant. We can go ahead and put the d theta out front. That part won't be too hard if it ever shows up. There we go. Times integral from 0 to 1 over root 2. This is really weird trying to write blind. I'm not sure why it's doing this. Alright, you won't be able to tell much of a difference, so I'm going to pause this video and see if that helps. Alright, so literally I just paused it for a couple seconds. We'll see if this works because there was nothing else running on the computer to slow it down, so I'm not sure what's going on. Let's see. Nope, still lagging. Oh well. Guess we'll just have to deal with it as it comes. Which unfortunately is going to make this video much longer than it's supposed to be because I'm waiting forever for this thing to write. Alright, square root 1 minus r squared minus r dr. Alright, doesn't seem to be too bad. Let's knock on wood. Let's see. Alright, this part over here, again, this is easy. This is 0. Theta goes from 0 to 2 pi, so that's just going to be 2 pi. Just remember to keep bringing that down. Alright, this one right here is going to require some u substitution. Really what we're going to have to do is distribute the r. So we'll have r root 1 minus r squared dr. The minus r squared, we could definitely separate the integration here. The minus r squared will be easy. It's this piece right here that's going to require the u substitution. So let's go ahead and do that over here. So u is going to equal 1 minus r squared. So du is negative 2r dr. And that makes dr du over negative 2r. Now we are going to have to go back to 1 over root 2 here because I don't want to change both of these. So that is going to give us an integral of r square root of u. The new du here is going to be du over negative 2r, and then minus this integral right here, which we'll go ahead and do in a minute. So again, bring down the 2 pi. So this one, r's are going to go away. I can pull out the negative 1/2, and that leaves me with an integral of u to the 1/2 du minus an integral of r squared dr. So 2 pi times, this is going to be, what is that, u to the 3/2, so 2/3 u to the 3/2 minus, what is that, 1/3 r cubed, and then I got to change this back into terms of r, so these 2's are going to go away. Negative 1/3 1 minus r squared to the 3 halves minus 1/3 r cubed, all of that from 0 to 1 over root 2. And again, don't forget to multiply the whole thing by 2 pi. All right, so let's see what we get. 2 pi, let's see, plugging in 1 over root 2. This is going to be a mess. Let's factor out the negative 1/3. So plugging in 1 over root 2, 1 over root 2 squared is 1/2. 1 minus a half is a half. So that's 1/2 to the 3 halves power. 3 halves power. Try that again. And then plugging in 1 over root 2 here, 1 over root 2 cubed is 1 over root 2 times 1 over root 2, which is a half, times another 1 over root 2. So it's really going to be 1/2 of 1 over root 2. So minus 1/2 of 1 over root 2. And then fortunately, plugging 0 into here gives us 1. 1 to anything is 1. Plugging 0 into here is 0. So really this is minus 1 after all that. So if I did everything correctly, let's see if this works. That'll be 2 pi. So actually, let's go ahead and multiply the negative 1/3 out here. So that's going to make that negative 2 pi over 3. And then I've got 1/2 to the 3 halves power minus 1/2 times 1 over root 2. 1/2 to the 3 halves power. So 2 times root 2 is 2 to the first times 2 to the 1/2, which is 2 to the 3 halves. Really, that's what you get down here, and the bottom is also a 2 to the 3 halves. So it looks like, if I'm doing this correctly, it looks like I'm going to get a 1 over 2 to the 3 halves minus a 1 over 2 to the 3 halves. There should be an extra parentheses there. Something's not right. Okay, I got it. I see it. At least I thought I did. Yeah, okay, I factored out a negative 1/3, which makes this plus. Okay, that makes more sense. Makes that plus. Maybe it still doesn't, because that's going to give me 2. No, it does. Okay. So that's going to be 1 over 2 root 2 plus 1 over 2 root 2 minus 1. But 1 over 2 root 2 plus another 1 over 2 root 2 is 2 over 2 root 2. So we get 2 over 2 root 2 minus 1. Of course, the 2's here cancel out. So what I get is negative 2 pi thirds times 1 over root 2 minus 1. And that is the volume that lies in between the top part of that sphere and the top part of that cone that's embedded in the sphere. And you might look at this and think to yourself, well, wait a minute, that's going to give you a negative volume. It's not, because 1 over root 2 minus 1 is also negative. So these two negatives will multiply together and give you a positive. All right. All right, because we are already pretty much at 20 minutes, we're only going to do a couple more of these. I'm going to get you started on a couple of them. I don't want this video to go more than about 30, so a couple of concepts I want you to get to. We're actually going to show that we can use a double integral to find the volume of a sphere. Now, one thing you should remember is that a volume of a sphere is 4/3 pi r cubed. And if you didn't remember it, there it is. So again, if you think about it, Here's your sphere. And really what we're going to do is we're going to focus on the top half of this sphere. So we're not really going to worry so much about this bottom part. We're just going to focus on the top half of the sphere. So we know that a sphere, the domain in 2 dimensions, is simply going to be a circle. And we're going to call the radius capital R, since we're just going to do this for any sphere that's centered at the origin here. And we know that the equation of a sphere centered at the origin is x squared plus y squared plus z squared equals our radius squared. And if we wanted to put this into terms of polar, first of all, we're going to solve this for z. So z squared equals capital R squared minus x squared minus y squared. Factor out the negative here, and we'll have x squared plus y squared. And then we'll take the square root, and we're going to get the square root of r squared. Again, that's going to be minus this x squared plus y squared. We'll call little r squared here because that'll be the polar of x squared plus y squared. So if we just wanted to do this, let's focus on the top half. We know if we find the volume of the top half, then we can find the volume of the entire thing by doubling it. So if I do this, we're going to go from, theta will go from 0 to 2 pi, right? Full circle. The radius is going to vary from 0 out to capital R. And we're going to have to double that because right now that's only going to give me the top half of this thing. And our function is this z, which is square root of capital R squared minus lowercase r squared r dr d theta. Now the one thing we cannot do is we cannot split this one. Fubini's theorem will not work here because r here is not, oh no, I'm sorry, r is a constant. Yeah, we're treating r as a constant because it's just the radius of whatever the sphere is. So we actually can use Fubini's theorem. So let's see, we'll have 2. The theta part will come out here, so 0 to 2 pi of d theta times 0 to capital R of square root of capital R squared minus little r squared r dr. So again, this part, like always, is pretty easy. That's going to be 2 times, and then that'll be theta from 0 to 2 pi. Let's go ahead and finish this one off. Plugging in 2 pi here, you get 4 pi because 0 gives you nothing. So it's 4 pi times whatever we get over here. Again, we're going to have to use a little bit of a u sub. So in this case, u is going to equal the inside of this, which is capital R squared minus little r squared. Remember, this is with respect to little r, so when we take du, that's a constant. It's gone, so it's minus 2r dr, making dr du over negative 2r. So I'm just going to stay in red here. So this is going to be the square root of u times r times my new dr, which is du over negative 2r. Those r's right there go away. I can factor out or pull out the negative 1/2. This antiderivative is going to be easier if we write it as u to the 1/2 du. So we'll have 4 pi times negative 1/2. The antiderivative of this, of course, is 2/3. U to the 3/2, but u was this. And then we'll evaluate that from 0 to capital R. So this is going to go away there. So you can see that we're going to have a 4 pi over 3 here. It's going to be negative for now. And that's all these constants combined. And then we're going to go ahead and evaluate. So if I plug capital R in for little r, it means I'm going to get a capital R squared minus r squared. Well, that's 0. And if I plug 0 in, it means I'm going to get a capital R squared to the 3/2 power. And then raising an exponent to an exponent, we multiply the exponent. So what I end up with here is negative 4 pi thirds times negative r cubed Multiplying these two things together, the negative times the negative goes away. So what we end up with is 4 pi, or excuse me, 4/3 pi r cubed. And there you have it. All right. The next one, we're not going to do the volume of a cylinder. We'll skip that one. Again, that's something if somebody wants me to do a video at a later time, I can. This one's kind of something that needs to be at least looked at and started, so we'll go ahead and do this one. Might take us over time, but we'll see how this goes. So here's the idea. It says a swimming pool is circular with a 40-foot diameter. So it's got a circular pool with a 40-foot diameter. The depth is constant along the east-west lines and increases linearly from 2 feet at the south end to 7 feet at the north end. Find the volume of water in the pool, or basically just find the volume of the pool. We're assuming the water fills the pool up to the whole thing. So here's what you kind of have to think, and I'm going to do this relatively quickly. The pool has a 40-foot diameter and it's circular. So that means if we kind of centered it right here, it would go 20 feet in either direction everywhere. So the top of this pool is going to be some kind of a circle, which looks something like that. That's, it's three-dimensional, so it's not a perfect circle from that perspective. But and then it says it's going to be 2 feet deep on the south end. We'll call this the south end. So that distance right there is 2 feet. And it's 7 feet deep at the north end. We'll call this the north end. East and west, it does not change. It does not go up. It does not come down. It doesn't go down this way. It doesn't, so this is basically the same. But what's happening is this thing is sloping upwards as it goes from here up to there, from the south end to the north end. It's got a slope. Now you can kind of see that slope. We know that the circular region on the XY plane is basically going to be the same as this circle right here. So it's going to be a circle with a radius of 20, it looks like, because if the diameter is 40, it's going to have a radius of 20. And it's going to go all the way around. So we know we're going to set up our volume to be 0 to 2 pi, 0 to 20, because again, from here out to all the edges is supposed to be 20, of z, which is our f of xy, r, dr, d theta. Well, the biggest thing is, what is z? Well, we can get that from the fact that this says the constant along the east-west line, so that this way it doesn't change, but it increases linearly from the south from 2 up to 7. Well, this gives us a slope of a line. And then from here we can use either this point or this point to write the equation of the line, and that'll give us our z value. So let's see, the slope here is going to go from, let's see, slope in this case is going to be the change of the z value over the change in the y direction. So the change in the y direction, see, in this direction right here is going to be, what is that, 40? Right, negative 20 to 20 is a 40 difference, and the change in z goes from 2 up to 7, so that's 5. So it looks like we're going to get a slope of 1/8. And then again, I can use the fact that this point is the point 720, so we know we're going to basically have, it's like y equals mx plus b, except in this case it's z equals 1/8 y plus b, because it's in the zy direction. So I can use the fact that this is 7 is z and 20 is y. To find my b value. So 20 over 8, what is that, 5 halves? Subtracting 5 halves from 7, 7 is 14 halves, so that should be 9 halves equals b. So what I get is z equals 1/8 y plus 9 halves. So this is what I'm going to integrate. So again, it'll be 0 to 2 pi, 0 to 20, 1/8 y plus 5 halves, I'm sorry, 9 halves r dr d theta, but of course y is in Cartesian, so we need to change that. 0 to 2 pi, 0 to 20. That'll be 1/8 of r sine theta plus 9 halves r dr d theta. And the theta and the r are separable. These are all constants, so you could use Fubini's theorem here. I am not going to go through the entire integration here because we are running really long on this video, but you should end up with 1800 pi for your volume of whatever this swimming pool looks like underneath of that. Okay. All right, this one here, again, I'm only going to go through a little bit of this as far as concept is concerned, and then we're going to actually stop. I'll give you what the answer should be on this one, but the last two I am definitely not going to do. So conceptually on this one, it says, use a double integral to find the area of the region of one loop of the rows r equals 3, cosine 3 theta. So if you remember back to when you did polar in AB and BC, we dealt a lot with these roses. If you don't remember what they look like, it's okay. I'm going to remind you, and you could very easily use your 83 or 84 to figure this out. But this is the interesting thing right here. They're having us use a double integral to find area. What we're used to is a double integral. That was horrible. But a double integral usually gives us volume. Well, how in the heck are we going to use a double integral to find area? Well, if you really think about what's happening, if you use the double integral, you're really finding the two-dimensional area on the xy plane. That means if we're going to use a double integral to actually find area, that means your z value has to be 1. That's all it really means. Or your height is 1. That's all it's indicating. So if we're going to use a double integral to find area, that means z, or your height, has to be 1. All right, so let me show you again what these loops look like. And this one, r cosine theta, looks something like this. It's got one loop that comes out like this, and then the other loops kind of do something like that. Something like that. They are all supposed to be symmetric. I did not draw it very well. But this is what cosine of 3 theta looks like. All right, so let's see how we're going to figure this out. What we should be able to do is figure out what one part of this thing looks like right here, because we're only looking for one loop. So if we can figure out this top piece right here, we can double that and figure out the entire loop. Well, so what we really need is we need to know what this angle is, because we're going to have to figure out what we're going to have to integrate from here to wherever. And the fact that this thing right here, if I go all the way into here, r, the radius is nothing. Now the radius changes. The radius is going to go from here and here and here all the way back to 0, but it's going to start way out here. It looks like at about 1. It could be 3. I'm not exactly sure. We'll figure that out in a second. But it's going to go from 0 all the way out to here. But this part right here is the curve. I mean, that's actually what this is. This is the curve cosine of 3 theta. So I'm going to have to figure out the angles that go with this. This is going to go from 0 for sure up to whatever angle this thing is. And this was what was called a tangent at the pole. We'll have to figure out what that is. Remember that this is going to have an r dr d theta in it. All right. So I do know that my r is going to go from 0 out to cosine of 3 theta. And remember, this is just r dr d theta because z has to be 1 here. have to have a height of 1 or a z-value of 1 in order for this to be area. It's what we're going to do here. Now I do know I'm going to double it because that's going to be, this is only going to be half of it. So let's see if we can figure out what this has to be. Well, if r has to be 0, if the radius has to be nothing here, I'm just going to plug 0 in here and find out what angle gives me that. So we're going to set 0 equal to cosine of 3 theta. Now I know that cosine equals 0 at pi halves. So really what I want is I want pi halves to equal 3 theta. Whatever this angle is needs to be pi halves. But then, of course, solving for theta, dividing both sides by 3, we get that theta is pi 6. So the angle that actually creates this radius right here of 0 is pi 6. So we're going to go from a radius of 0 to pi 6. I'm sorry, theta of 0 to pi 6. And then we're going to double it. And that'll give us the area of one of these loops right here. All right, and again, this one is not separable. This is not constant, so you cannot use Fubini's theorem here. I know the video is going to be almost 40 minutes, but I think we should at least go through some more of this because you're going to need these things, which you may or may not remember, but this is a couple of identities from polar. Cosine squared simplifies to 1/2 1 minus cosine of twice the angle. And then sine squared is 1/2 of 1 plus cosine of twice the angle. And yes, these are both cosine. The only difference is this one is minus and this one is plus. So cosine is minus, sine squared is plus. So here's what's going to happen. We're going to have to integrate with respect to r first. So we're going to get 2, 0 to pi 6. That's going to give us 1/2 r squared from 0 to cosine of 3 theta d theta. The 2 and the 1/2 are going to go away. So I'm going to have 0 to pi 6. See, r squared is going to give me cosine squared of 3 theta. Plugging in 0 gives me nothing. So d theta. This is why we need this guy right here. So now I'm going to rewrite this as the integral from 0 to pi 6 of, using this reduction formula, it's 1/2 1 minus cosine of twice my angle. My angle is right now 3 theta, so it's going to become 6 theta d theta. I can pull the 1/2 to the front. And actually, let's just erase this. I'm going to pull the 1/2 to the front, and then I'm going to take the antiderivative. Antiderivative of 1 is theta. Antiderivative of cosine is going to be sine of 6 theta, but I have to multiply it by the reciprocal of this, which is going to be a 1/6. That's a shortcut to not doing the full u substitution from 0 to pi 6. All right, so let's see. 1/2 out in the front, plugging in pi 6 will give me pi 6. Plugging in pi 6 here gives me sine of pi, but that's 0. Plugging in 0 gives me 0. Plugging in 0 here gives me sine of 0, which is also 0. So that's really nice. All that stuff went away. So really what I get is pi 12ths. All right, much, much longer than I wanted it to be, so I apologize. It's about a 40-minute video. Again, if anybody wants me to do the other problems, they are good problems. They are something interesting to see, but not really necessary.